Alright, so in this video I'm gonna be explaining this important article with the title Learning Substructure Invariance for Out-of-Distribution Molecular Representations. This NeurIPS paper in 2022. Molecular representation learning has been extensively studied, and current methods have shown promising power for various tasks such as molecule property prediction and target identification. However, a common hypothesis of existing methods is that either the model development or experimental evaluation is mostly based on IID data across training and testing. Such a hypothesis can be violated in real-world applications where testing molecules could come from a new environment, bringing out serious performance degradation or unexpected prediction. We propose a new representation learning framework entitled MOL-OD to enhance the robustness of MRL models against such distribution shifts. Motivated by an observation that the biochemical properties of molecules are usually invariantly associated with certain privileged molecular substructures across different environments, such as scaffold, sizes, and etc. So we introduced an environment inference model to identify the latent factors that impact data generation from different distributions in a fully data-driven manner. We also propose a new learning objective to guide the molecule encoder to leverage environment invariant substructures that more stably relate with labels across environments. So biochemical properties of molecule are usually associated with a few privileged molecular substructures. To achieve robust molecular representation for out-of-distribution generalization and overcome potentially unreliable environment labels, we devised a new MRL framework. So we first formulate the out-of-distribution generalization for molecule property prediction by introducing a latent variable for environment that affect the data generation. Then we analyze the essential cause behind the failure of existing MRL models. So training has two steps. First, we optimize an environment inference model from training data, and second, we optimize a molecule encoder and a predictor. So you know about out-of-distribution generalization, this min-max of expectation of the loss. And this expectation is often called risk function, because if in different environment, you can define this risk function, condition on the environment. We can minimize the maximum of expectation of loss. So we want to find an invariant predictor that could uncover invariant relationship between inputs and outputs, between inputs and targets across all environments. So the maximization is across all environments. So the invariant predictor aims to learn an invariant representation satisfying such an invariant principle that first we want to have sufficiency, showing that sufficient predictor power for target. And then we want invariance contributes to equal performance for the downstream tags across all environments. So sufficiency and invariance, if you keep this in mind, then they talk about molecule representation learning. These are the backgrounds that we need to know. because existing molecular representation learning methods can be classified into two categories. The first is SMILES-based, where SMILE refers to simplified molecular input line entry system. And they use language model to process the textual representation. Existing general out of distribution generalization methods are not tailored to such non-Euclidean structured data such as molecules. So in several recent works, the importance of molecular substructures has been emphasized, and such inductive biasing is incorporated into the design of those models. So what is the methodology? The out-of-distribution generalization is on molecular representation learning. So we have a molecular graph which can be represented as G. The training and test data are separated, and the goal is to predict the target label Y. So out of distribution generalization problem is just this min-max. But the framework contains two parts. The front-end molecular encoder, this phi, for learning an invariant representation of input graph, and the back-end predictor omega. So both phi and omega should be discovered in this optimization problem. And solving this number two, solving this min-max of expectation of loss is intractable in practice, since we cannot know all environments. For example, we cannot have a complete support set. So we resort to minimizing the expectation of risks from different environments known in the training data. And this symbol here is just showing the probabilistic independence. All learnable parameters of the molecule encoder and the predictor are included in theta. So the probabilistic independence between Y and the environments, given your phi, can be achieved via minimizing their mutual information. Here is just mutual information between them, between your Y and the environment. So treating the outputs of the omega and phi as distribution can be specified like this. So we have arrived at a clear but still intractable optimization. So given prior of the environment distribution, we need to maximize the log likelihood of probability of Y condition on G, and then obtain the posterior, which are parameterized by tau. And we know this evidence lower bound that we can write our loss like this, because our goal is to minimize the Kullback-Leibler divergence between those two distributions, Q and P. So this is a common paradigm that we see in machine learning. But this is an overview of our model. The whole training procedure is divided into two stages. We optimize the environment inference model given an input molecule G. We first infer the latent variable, environment variable E. So we want to infer the distribution over this environment. And We call it environment classifier. Also, we have a conditional graph neural network. We can have distributions of y conditioned on that environment. So for different environment, we want to see what is the probability of each environment. And this stage is trained under the guidance of elbow. So let's look back into objective and give an equivalent tractable objective. So this loss should be minimized. And G sub E consists of pairs of molecule graph and the corresponding label Y. So we have a query, and then we have, using attentive pooling, we can have a prediction. So this is the algorithm that we assume that we have given a data set, number of training epochs. So we go through this, that we sample data batches and they compute batch loss, and then we backpropagate. Then we freeze the parameters, what we learn. And now that because we have frozen the parameters, we sample batches again, but now we have to determine the environment that we sample. So what is the argmax? Which environment maximizes this probability? And then we backpropagate L of inverse. So here we L of elbow, we freeze it, and then we backpropagate for the loss of inverse. And then they compare different methods, and this is out of distribution generalization. So you see here in the appendix, they talk about a causal perspective.